Nuclear reaction. In nuclear physics and nuclear chemistry, a nuclear reaction is semantically considered to be the process in which two nuclei, or a nucleus and an external subatomic particle, collide to produce one or more new nuclides. Thus, a nuclear reaction must cause a transformation of at least one nuclide to another. What are nuclear reactions? Nuclear reactions are processes in which one or more nuclides are produced from the collisions between two atomic nuclei or one atomic nucleus and a subatomic particle. The nuclides produced from nuclear reactions are different from the reacting nuclei, commonly referred to as the parent nuclei. Two notable types of nuclear reactions are nuclear fission reactions and nuclear fusion reactions. The former involves the absorption of neutrons, or other relatively light particles, by a heavy nucleus, which causes it to split into two, or more, lighter nuclei. Nuclear fusion reactions are the processes in which two relatively light nuclei combine, via a collision, to afford a single, heavier nucleus. Processes that are not considered to be nuclear reactions. The term nuclear reaction is generally used to refer to the externally induced changes brought on to atomic nuclei. Therefore, the following processes cannot be classified as nuclear reactions. Nuclear scattering processes, processes that involve the collision and subsequent separation of atomic nuclei without any notable changes in the nuclear composition. In these processes, only momentum and energy are transferred. Nuclear decay, a process through which an unstable nucleus emits radiation in order to lose energy. Spontaneous fission reactions, nuclear fission reactions that do not require a neutron to proceed and are, therefore, not induced. These processes are quite similar to nuclear reactions, but are spontaneous rather than induced. Why do nuclear reactions release tremendous amounts of energy? The mass of an atomic nucleus is always less than the sum of the individual masses of each subatomic particle that constitutes it, protons and neutrons. This difference in mass is attributed to nuclear binding energy, often referred to as a mass defect. Nuclear binding energy can be defined as the energy required to hold all the protons and neutrons within the nucleus. During a nuclear reaction, such as a fission or fusion reaction, the mass accounted for by the nuclear binding energy is released in accordance with the equation E equals mc square. Energy equals mass times the square of the speed of light. To simplify, the products formed in nuclear fission and nuclear fusion always have a lower mass than the reactants. This missing mass is converted into energy. A single gram of matter can release approximately 90 billion kilojoules of energy. Nuclear fission. Nuclear fission refers to the splitting of an atomic nucleus into two or lighter nuclei. This process can occur through a nuclear reaction or through radioactive decay. Nuclear fission reactions often release a large amount of energy, which is accompanied by the emission of neutrons and gamma rays, photons holding huge amounts of energy, enough to knock electrons out of atoms. Nuclear fission was first discovered by the German chemists Otto Hahn and Fritz Strassmann in the year 1938. The energy produced from fission reactions is converted into electricity in nuclear power plants. This is done by using the heat produced from the nuclear reaction to convert water into steam. The steam is used to rotate turbines in order to generate electricity. Examples. An important example of nuclear fission is the splitting of the uranium-235 nucleus when it is bombarded with neutrons. Various products can be formed from this nuclear reaction, as described in the equations below. Uranium-235 plus 1 neutron 141 barium plus 92 krypton plus 3 neutron. Uranium-235 plus 1 neutron 144 xenon plus 90 strontium plus 2 neutron. Uranium-235 plus 1 neutron 146 lanthanum plus 87 bromine plus 3 neutron. Uranium-235 plus 1 neutron 137 tellurium plus 97 zirconium plus 2 neutron. Uranium-235 plus 1 neutron 137 cesium plus 96 rubidium plus 3 neutron. Another important example of nuclear fission is the splitting of the plutonium-239 nucleus. Nuclear fusion. In nuclear fusion reactions, at least two atomic nuclei combine/fuse into a single nucleus. Subatomic particles such as neutrons or protons are also formed as products in these nuclear reactions. Nuclear fusion reaction. An illustration of the nuclear fusion reaction between deuterium-2H and tritium-3H that yields helium, 4He, and a neutron, 1N, are provided above. Such fusion reactions occur at the core of the Sun and other stars. The fusion of deuterium and tritium nuclei is accompanied by a loss of approximately 0.0188 AMU of mass, which is completely converted into energy. Approximately 1.69 times 109 kilojoules of energy are generated for every mole of helium formed. Nuclear fusion examples. The reactions which take place in the Sun provide an example of nuclear fusion. 1 hydrogen plus 2 deuterium 3 helium. 3 helium plus 3 helium 4 helium plus 2 1 hydrogen. 1 hydrogen plus 1 hydrogen 2 deuterium plus 1 beta particle. Distinguishing between fission and fusion. Both fission and fusion release enormous amounts of energy. Both fission and fusion reactions can occur in nuclear bombs. So how can you tell fission and fusion apart? Fission breaks atomic nuclei into smaller pieces. The starting elements have a higher atomic number than that of the fission products. For example, uranium can fission to yield strontium and krypton. Fusion joins atomic nuclei together. The element formed has more neutrons or more protons than that of the starting material. For example, hydrogen and hydrogen can fuse to form helium. Fission occurs naturally on Earth. An example is the spontaneous fission of uranium, which only happens if enough uranium is present in a small enough volume, rarely. Fusion, on the other hand, does not occur naturally on Earth. Fusion occurs in stars.